Hello, everybody. I'm Bingqing Wei of Mechanical Engineering Department at the University of Delaware. I would like to share with you today on the photocatalytic hydrogen production from water through photothermally induced biphase systems. So at the beginning, I would like to acknowledge my collaborators, Dr. Shaohui Guo, Professor Shenhua Li from NPU, and Professor Zhu Li from MIT. So today that we encounter, both energy crisis and the environmental problems, and that need to be solved. And as you can see that, there's two aspects. First, it's the energy. So we kind of lack of, renewable or clean energy. The second, that's suppose if we still use traditional fuel energy, so that will generate a big environmental problem as we just experienced in the worldwide. So like, it's extremely, weather, so flood, extremely cold, extremely hot, so that we have to do something that try at least slow down this, environmental pollution case. Well, there's tons of, strategy have been proposed in the past, decades that try to use renewable energy that try to improve our quality of our life. And that these renewable energies can come from, many resources, for example, that solar, wind, and also nuclear, so many of them. And one of the, approach that have been, proposed and investigated quite intensively is the photocatalysis technology. So as you can see here, people lay out the vision of the future community based on this technology. So basically can influence any aspect of our daily life. And in this photocatalysis technology, there's one method that try to convert solar energy to hydrogen energy by water splitting technique. So in fact, hydrogen economic has been investigated for a few decades, and that hydrogen is a very useful fuel, and emit zero pollution if you use it quite effectively. And also that related to many of our daily lives. So from closing food to power housing and also transportation. So how to get this, clean hydrogen? Well, there are mainly three solar water splitting system has been proposed and people invest a lot. So for example, that one is a photovoltaic assisted electrolysis. So in this technique, of course, there's solar to hydrogen efficiency can be as high as 30%. However, that you have to build this solar panel that access this electrolysis process. So in this case, the cost is extremely high. And another one is for the electrochemical cell that even you provide solar, however, you have to provide extra voltage that can help. So like hydrogen evolution reaction or oxygen evolution reactions. So in both the system, that the costs are extreme high. So of course, Department of Energy that proposed that accepted cost for hydrogen production that should be, just a couple of dollars. So in this case, another system called particular photocatalysis method have been, into the picture that can meet this cost effective requirement. So basically, you just disperse this particular, photocatalyst in water, and that based on this solar irradiation, that you can produce, gases like especially hydrogen. So this process is very cost effective and also very simple, and that is a low maintenance as well. So particular photocatalysis has a huge potential for practical application. However, this solar to hydrogen, conversion efficient is extremely low. So in other words, there's a lot of space that you can improve to increase this efficiency. And people try to, improve the efficiency by, basically the 3 steps. So that all related to this hydrogen production steps. So first, the light absorption from water, because some materials has a very narrow absorption range, and also that's how to improve the low quantum efficiency, and that try to effectively separate the charges generated, and also transportation transfer this charge. So try to lower down this recommendation process. And the third will be the catalytic reaction itself. So how to improve the reaction efficiency as well. Well, there's plenty of smart strategies have been proposed and demonstrated in the past decades. Try to improve the hydrogen production by either plasmonic effect, and also structure and defects engineering, and as well as doping elements. So all of them seems to focus on the catalyst itself. And there's no research that's tried to view from different angles. So in all the strategy, basically, that's for light absorption is try to broaden and to get the broadband absorption and enhance absorption intensity. That's have been achieved quite significantly. And related to the low quantum efficiency, the people try to enhance the exciton generation and also the facilitate the exciton separations. And of course, for the catalytic reaction, so try to enrich the catalytic active sites. So my topic will focus on this part today, and in particularly different from the previous strategy focus on catalyst itself. We try to regulate the interface about this catalytic reaction by generate photothermally generate a biphase system. So you might curious what's a biphase system? Well, that's quite straightforward. Basically, we just simply replace the liquid water to gas water. So that's a steam. So in the traditional system that we call this a triphase reaction system, basically you have the liquid water, a solid catalyst, and produce the hydrogen gas. So there's a 3 different phases: liquid, solid, gas. And the new system, however, that we have replaced this liquid water with gas water, and at the same time that we have reduced the phases from 3 different liquid, solid, gas phase to, gas phase plus, solid phase. So simply change from triphase system to biosystem, you can dramatically improve their performance. The reason is that in the traditional, triphase reaction system, so from both kinetic and thermodynamic perspectives, so like for example, low reaction rate, high hydrogen transport resistance, and also that's a very high reaction energy barriers existed. In the new system, so just simply replace the liquid water to gas water, so you can improve the conversion efficiency by 20 times. Just give you an example here. So we simply compare this liquid water and the steam, that you can see this solid to hydrogen efficiency from triphase 0.3% to more than 6%, so more than 20 times higher. That's of course related to the hydrogen evolution process. That also increased by 18 times. So that just simply give you the example to show this. So what factors basically improve this catalytic reaction in this system? That also very straightforward. We test a few of them, and for example, the flow rate of steam have a significant impact on the production of the hydrogen. So like the schematic, the figure show here. So this is a rate of hydrogen evolution as a function of steam flow rate. So you can see that with the flow rate increase, the hydrogen production rate also increase. However, that will reach or saturated once reach a certain speed. For example, that at about 80 milliliter per hour, so we reach pretty much optimize this hydrogen evolution rate. And other factors you can easily imagine, so like a temperature effect. Temperature effect through two different perspectives. So one, the thermodynamics, of course, that can reduce the reaction absorption barriers. Like for example, through the calculation, we simply compare, so in this case, both liquid water. So in this case, you can see just simply increase temperature, you reduce the absorption barriers for hydrogen. So for water molecule in this case, and also that's hydrogen molecules also reduce their energy. From the kinetics perspective, that you can easily imagine that can easily accelerate the reactant molecules collision frequency. So like the experiments show here, so that you can see that you just simply increase the temperature, you increased solid to hydrogen efficiency, and that curve can be easily fit and with this equation. And based on this, suppose if up to 100 degrees C, that is the kind of melting temperature for water. So this solid to hydrogen efficiency, can be up to about 2%. However, as I show you here at the beginning, so we can, in our experiment, that we can reach more than 6% this efficiency, and that means in addition to the temperature effect, so there are other determining factor, so that play a crucial role here. So this is the phase effect. So phase effect is means from liquid phase to gas phase. Let me show you some simulation result that we get. So from a thermodynamic perspective, that again, that reduce the reaction absorption barriers significantly. So for example, the water molecule absorption on the catalyst, you can see, in the biosystem. So this, Gibbs energy is kind of change from positive to negative. So it means, this reaction happen automatically. And at the same time, to produce the hydrogen molecule absorption, or desorption is kind of a favorite to hydrogen desorption from the solid catalyst. So this from thermodynamic perspective. From kinetic aspect, this phase changing also dramatically boosts the hydrogen diffusion coefficient. So simply calculate hydrogen diffusion coefficient in both liquid and the gas phases. You can see this diffusion coefficient increase by nearly 50% times if you just simply change the phase. Okay, so that's significant, right? So in that case, that I hope I convince you that simply change the phase from this liquid water to gas water, so you can dramatically increase solid to hydrogen production coefficient efficient. So how to produce steam efficiently or cost effective? Again, there's many methods that you can use to produce steam water, like using electricity, fuel, geothermal energy, and also solar. So the one thing that's that probably is quite interesting is, again, that you don't need to apply extra energy by simply apply solar. There's a concept proposed, demonstrated a couple of years ago. It's from solar to steam. So as schematic show here, so that you have light in and you have vapor out, right? So several research groups proposed the same idea for this solar steam generation. So in fact, that's one material that's particularly interesting in this solar steam generation. That is wood. It's a natural wood because the structure is unique, and also the material is unique, so that wood structure can be used directly to achieve solar-driven steam generation. Okay. So let me show you that's simply just a pine wood structure here. So you can see that the max structure of the pine wood, you can see there have a kind of a micron scale. Typically, it's about 20 microns inside the channels, and that can driven the water molecules and absorb water molecules or through these channels. And this is a top view, and this wood growth direction. You can see this channel is through channels. So you just simply cut a piece of wood, and at the same time we realize that if you kind of treat the surface of the wood, basically it's kind of from nature wood to kind of char, or in other words, carbonize the surface, not all the piece through the piece of wood, but just the surface. So the function of this, basically you can either enhancing light absorption because carbonized surface become black, absorb light more efficient. The second, the lower part of wood also maintaining the water availability, so that you need to have an interface between the wood and water, so that you can continuously attract water molecules through the wood structure. So that is the purpose. All right, the preparation of this pieces means integration of the wood and the photocatalyst. It's very straightforward, very simple, as a schematic show here. So you have piece of wood and do some surface treatment like a carbonization. And you can simply use a spin coating method to coat the catalyst into the pore structure of the wood. And after that, you just put the piece under light, and you can have the steam generated. At the same time, you get hydrogen gas. So let me show you some examples. We test carbon oxide, and carbon oxide catalyst is one typical catalyst for this particulate photocatalytic reaction. And the size is about 15 nanometers in diameter. And not only carbon oxide, we also test other catalyst materials as well, like molysulfide, carbon nitride, and titanium oxide. So let me show you some results. And here I should mention that when you flow this carbonized wood piece with the catalyst, you need to make sure this catalyst only exposed to steam water, not liquid water. How to control that? So here we, for example, if you cut a piece with thickness of about 5 millimeters, and so basically we test the spin coating that the catalyst distribute to the depth about 2 millimeters into the wood. That we have evidence from the Raman spectroscopy. For example, the molysulfide we test, and you can see that for each of the steps is about 500 microns. So that's only the first, four signals. You can see this molysulfide. Otherwise, there's no molysulfides, in the deep space. Means, molysulfides only distributed within the top 2 millimeters. So that you need to make sure this catalyst only exposed to the steam. The reason is that, this wood pieces, will be, sucked into the water. That is about 2 millimeters as well. So, and you can also see that by, coating this molysulfide, there's reflection of the, this light also dramatically decrease. So that's its good thing. Well, so let me simply provide some experimental evidence to show you that this strategy for producing hydrogen is most efficient, and also showed excellent performance compared to other systems. And this one is we use molysulfide. So again, that's simply compared to Triphase case. So the hydrogen production increased by about 15 times. Not only that, but also that the stability of the catalyst. So we test, we examine molysulfide attachment to the wood structure. And as you can see here, before the reaction and after the reaction, there's no big difference, And then also we test, it's a possibility that, molysulfide will detach from wood to water. Well, we test the bulk water after, reaction for some time. And we test quite a trace amount of moly signal, but indication they have a small amount of moly detached from wood structure, but not significant amount. And let me give you another example, by using copper oxide catalyst here. Again, of course, you need to figure out what might be the optimal, catalytic loading. In this case, so we found that it's about 38 milligram per centimeter square that you have basically achieved the best performance for hydrogen production. Again, that compared to the triphase case. So the hydrogen production increased by 17%. And also we test the lifetime, again, that to see how stable the catalysts attach on the wood structure. And here we test, for continuous 5 days, 8 hours per day. And you can see the retention, the production hydrogen, retention up to 90%. So that, for all the demonstrate systems reported in the literature, it's hard to achieve such a good stability. And here we also test, for example, that before and after the reaction that you can see, the morphology and the particle size of the catalyst doesn't change much. So that again demonstrates the stability of this catalyst or the strategy. And here again to show that before and after reaction, so that elemental signal distribution on wood structure doesn't change much as well. That give you a direct evidence to show this good stability for this approach. So another, comparison that we summarize in this slide. And so we test 4 type of, typical photocatalysts, that's using our approach. You can see that, compared to other systems that reported in the literature, by using the same, catalyst, you can see, the two-phase, system by applying this wood structure all stand out compared to other systems. Okay, so that means the high efficiency can be achieved by using this approach. And compare not only this typical catalyst, and even with other, particular photocatalyst systems. And again, either, so metallic catalyst or maybe sometimes heterostructures, so that, this wood catalyst system showed the highest solid to hydrogen efficiency. We also try to, apply this system to heterojunction photocatalysis. Like, here we tried, copper sulfide, molysulfide heterostructure, and we achieved the highest, hydrogen production, rate. And again, so that, compared to Triphase system, this the biosystem increased by 16%, 16 times. And also the overall hydrogen production rate is the highest so far in this particulate photocatalysis systems. So we also tried try from a pure water to seawater and use natural sunlight as a photo show here. Here the system. This quite simple demonstration, and we apply here this copper sulfide, monosulfide, and use simulated seawater. That's about 3% of salt, and we can achieve solid to hydrogen efficiency about 3.4%, and also very, very stable. We measured 2 hours, 4 hours, 6 hours hydrogen production, and they are pretty much the same. All right, so in that case I will conclude here. I hope I've tried to convince you that we have that design and demonstrate the integrated photothermally induced photocatalytic biphase system. And we achieve a quite dominant photocatalytic hydrogen evaluation rate among all particulate photocatalyst system. And we simply regulate the phases by convert traditional triphase interfaces to this biphase interfaces. And also that we can simply apply this wood carry idea and this simultaneously convert liquid water to steam water and also the hydrogen production without additional energy input. So that's pretty much what I would like to discuss today. And I would like to thank you for your attention.